So our next speaker is Yan-Chuan Cai from the University of Edinburgh. Yan-Chuan has worked over the past decade. Recently, he worked together with two of our other speakers, Mark, as Mark already mentioned, and Miguel Aragon, on a very original paper in which they showed that, in fact, you can find the rotation of filaments, a paper that went along with a other publication by Elmo Temple and Noam Libeskind, where indeed they did find it in the data. But today, Chai is going to talk about basically splitting the cosmic web in order to find more information on the universe. And the floor is yours for the next 20 minutes.
Thank you, Ring, for the very kind introduction. And also thank you for all the organizers for having me here. It's deeply humbled to be in one of the centers that's dedicate themselves to study the cosmic web for a long period of time. And so my topic is about splitting the cosmic web for more information. And I would like to bring the audience, to taste a little bit of flavor on extracting information from a little bit more observational perspective from the cosmic web. And by information here, let me define, realize I have to draw the boundary here. So basically, this is information that we can learn about from the observations that we take from telescope data. So basically, information about our physical universe. So yeah, I'll give a probably unnecessary very brief introduction about the cosmic web, as Job and Mark have already laid down the stage here. And then I'll focus on talking about why we would like to develop more accurate modeling to learn about cosmic information, essentially the growth of structure in the cosmic web, and eventually what we can achieve by doing that. So this is sort of a cliche cartoon picture illustrating the entire universe. But the two things, to my understanding, that we can learn about is basically, one, the universe is expanding, as illustrated here through this picture. And the second thing is that structure are forming and they are growing. So from decades of campaign and observation and theories alike, we have reached consensus about this concordance cosmology. Basically, we think that we live in a universe that are hugely dominated by all these dark components, dark matter, dark energy, and just a small fraction of ordinary matter that shine lights and that allow us to see all these things are taking place. So once we know all the matter energy species in the universe, basically that sets the expansion history of the universe. But then the next thing that's probably a bit more interesting is about the growth of structure. And again, this is textbook equations. Basically, it's dictated by this set of equations here, the continuity equation, Euler equation, and the Poisson equation. So it seems in the Newtonian framework in the standard model, this is relatively simple, but it's actually rather complex to solve. So we can reduce it to the linear order, which we can solve fairly easily just by this one equation. But we know from Job's talk that the formation of the cosmic web is far from linear. So it is certainly far from enough. Now, in the last few decades, this embodied simulation or cosmological simulations in general developed really, really well. So that allow us to simulate or to visualize all this is taking place. So basically, we give the supercomputer the initial conditions and ask the computer to solve the equations that we ask them to solve. And we can see this evolution of and development of the cosmic web structure from the very early universe, where the universe is almost uniform with some tiny fluctuations. And later on, we get developed these concentration of matter, the clusters and superclusters, and emptiness of underdense regions, voids, and also filamentary structures that typically connecting pair of dark matter clumps. But of course, this is pretending that we see all of the matter distribution in the computer world. And in reality, what we can see is actually just the tiny bits of lights, the galaxies that they're hosted by these dark matter clumps. So this is, but if we have some approximately to populate these simulations with galaxies, then this is approximately what we will see. You can see that galaxies traces the cosmic web structure incredibly well. And it looks incredibly similar. And this is not only so in simulation, but you can compare those with contemporary surveys, such as the Sloan Digital Sky Survey. This is the map of the 3D number density of galaxies distributed, mapped out by Sloan. And you can see qualitatively, they look, to me, my eyes, and it looks like similar to what we can simulate from the supercomputers. So a bit more qualitatively, now the simplest thing you can do to draw out information from the statistics of the cosmic web is simply making a one-dimensional PDF of the density. So if you do so, the earliest observation we can obtain so far is the CMB. And as traced out by the temperature fluctuation, you will usually find that the early universe, the PDF of the density of temperature is extremely close to Gaussian. Whereas at the late time universe, traced out by galaxies, then you typically find that at intermediate scales, the distribution is far from Gaussian. It's actually close to a normal distribution. The next thing we typically do is to take it to the next order of moment, which is the variance, or the Fourier transform of this so-called two-point, the second movement, two-point statistics. So basically, that's the power spectrum. So if you take Fourier transform of the CMB, then you get this familiar power spectrum of the temperature fluctuation. And you can then wind the clock forward to make a uniform comparison with the late time understanding of the matter power spectrum traced out of galaxies and plot them together. And you see that this model prediction goes extremely close to those data points, and it's just almost spot on. And this is merely by exercising the so-called linear growth rate being perfectly known with the cosmological model being set. So by looking at this diagram, it looks like we have a huge success. The model seems to fit the matter perturbation across from the CMB up to the late time universe. And simply by knowing basically the matter energy contents of the universe with the assumption of concordance cosmology, we get it right. However, you notice that there's some truncation of data at this point, a few tens of megparsecs perhaps. And that's not because we don't have the data, but simply because actually we have no good model to go further down there. So this is simply the prediction from linear theory. So if we were to stitch these missing part from simulations, then the prediction would expect to deviate from linear theory prediction at a fair amount. And it is in this region where the complex cosmic web structure is forming and the development of the density perturbations become highly nonlinear and non-Gaussian. So we kind of live, to my understanding, living in a region where on the large scales, the modeling is relatively simple, is linear, but on the other hand, you see that these error bars are very big, and that's because to map out this large scale matter fluctuation, you need huge surveys or very deep surveys. Or on the other hand, on the small scales, there's a lot of information. As you can see, the error bars just keep shrinking because if you just do simple mode counting, then the number of available perturbation modes will go with k cubed. So one should expect a lot of information at the very small scales. However, at this region where we're essentially, as a community, we don't have the full capability to exploit all the available data in this region. So if you buy this argument, I would say that at least to making effort towards digging out more information, even just from the existing public data, is at least equally important as going for a bigger and deeper survey to harvest these large-scale perturbation modes. So this is the major domain that motivate the study I'm going to show you. So now back to learning about the growth of structure, mainly focusing on understanding or trying to extract information about this growth rate parameter F as it dictates the evolution of structure. Then we turn to look at these techniques called redshift space distortion. So in using galaxies to map out the cosmic web structure, what we realize is that the observed distance of a galaxy is not only dictated by the expansion of the universe, but also there's a peculiar velocity part that comes with it, and that's sourced by gravity. You can think of it as a perturbation to the true distance, but it's also at the same time a source of information for us to learn about the growth of structure. So around massive overdense regions, typically galaxies are driven by gravity to fall towards the center of the gravitational potential. Therefore, when we observe them along this line of sight, they would typically appear squashed along the line of sight. So therefore, this introduces an anisotropy for the observed distribution of galaxy on average around massive clusters. And it is true for this so-called two-point statistic, or the power spectrum or two-point correlation function, because that by doing so, by doing pair counting, we are forcing ourselves to center ourselves in the center of galaxies of density peaks. So this is known for a long time, since Kaiser 1987. So this is the redshift space power spectrum, or the Fourier transform of the correlation function. It can be mapped to the real space power spectrum with this bunch of parameters here. The key quantity here is this growth rate parameter F. So basically, by learning about the anisotropy of this galaxy distribution, that would allow us to learn about the growth rate of the universe. So this is to illustrate how it happens. So this is some approximate distribution of galaxies in real space. From simulations, you can see it's perfectly isotropic. But if then we pretend we observe the system from this direction, then this squashing effect takes place because of the infall, and around the center, in the extremely high density regions, this random motion, zero motion, just drive things to go even further. So just a side note about the redshift space distortion around void. This is closer to my heart, and also I believe to Rian and many here. It's probably obvious for you to think that around these relative underdense regions, galaxies will be falling apart from each other, and then we would naively thought that when we observe these systems, they will appear to be elongated. But not necessarily so. Even if you can also write down the equivalent of the linear theory, as in Kaiser, you'll find that the distortion pattern is typically quite complex, although it's perfectly predictable, even just from linear theory. But it's solely dictated by the density profile of the void. And again, this connects to the observed quantity, which is the redshift space void galaxy cross-correlation function with this growth rate parameter F. Now, this has been exercised. I mean, in general, redshift space distortion has been measured and been used as almost a standard tool in galaxy redshift survey for many decades. So this is an example from 2D F galaxy redshift survey. Back then, almost 2 decades ago, they look at the average, they do counting of pairs of galaxies around this redshift slice and average them. This is some similar to what I've shown you, the galaxy two-point correlation function in 2-dimensional transverse to the line of sight and the line of sight. You see this typical Cai squashing effect that comes with the info of galaxies, and also see the elongation around the center due to the random motion of galaxies. So the moment when you see that there's a distortion pattern here, usually this is the interesting interface that allows us to ponder and think back that there's information hidden there. So I would like to draw a not so appropriate analogy to art, where when artists paints a picture like this, I imagine on average person would probably think that these are distorted as well. So I think methodology-wise, when the way the artists use this distortion to kind of convey something perhaps about human nature is similar to the approach that we took in observing the distortion of this correlation function. And that in this way, in this domain, it allows us to learn about the growth parameter, basically. So more quantitatively in this study, I would like to focus on this, the constraint on this growth rate parameter, which is some combination of this omega m matter density and with the linear bias parameter, and to the 10th of percent level, and this is using around 0.1 million galaxies at the time. Whereas now, almost 2 decades later, SLOAN, a digital sky survey, increased the number of density that available to about 1 million, a factor of 10. But then if you look at the level constraint for this growth rate parameter in 3 Redshift slides, work out the numbers there, it's still hanging at the order of 10%. So this appears to be puzzling. So on this time span of over 2 decades, we seem to make little progress. And I would like to draw your attention to this, which is the fitting range that they use for this model fitting is around 8 to 25 megaparsecs in this relatively small survey. Whereas in this bigger survey, typically people stop at exactly 20 or 25 megaparsecs. So when we go about to harvest the huge data set from SLOAN, which allow a lot of statistical power to constrain cosmology, we seem to already been stopped by the ability, the accuracy of the modeling. And I believe that's one of the reasons why people stop here. I'm not pointing finger to any of the individual. This is, I believe, most of the papers written to use these large surveys have to stop somewhere here, because we just have essentially a lot of statistical power, but we just cannot afford to have a biased result, even tested with mocks. So to understand how we can go further from there, let's get back to one of the basic model approach here. So this again is just simply, this is where redshift space distortion starts, is the perturbation of observed distance by peculiar velocity. And back in 1980s, Peebles have written down this formula where this is connecting the real space correlation function with the redshift space correlation function, and basically saying that it's merely almost like just a convolution of the real space quantity with the distribution, the full distribution of the line of sight velocity. And that's fairly straightforward to understand. And then, but the reality is that knowing this, the full distribution of the peculiar velocity is non-trivial. And then in 1995, Fisher wrote down this so-called Gaussian streaming model, where basically by assuming that this distribution function has to be Gaussian, so that's why this whole blob is basically a Gaussian function. And there's 3 key ingredients needed for this modeling framework. One is, again, the real space correlation function, and then the streaming velocity as a function of radius, and also the dispersion of it. Obviously, this is a Gaussian, so knowing the dispersion is knowing everything. So with these 3 pieces of information in mind, we can go about to test how well this model can perform by comparing it with simulations. So this 2D correlation function is showing the measurement from simulations in black contours versus the model prediction in dashed curve. And with all the 3 key ingredients of the model measured directly from simulations. You can see overall this is doing really well, especially on large scales. However, you see around the central bit here, small scale, there are noticeable discrepancies, and this has been known. And it's also noticeable. This is not if you want to use information at around order of 10 megaparsecs ish. In the era of precision cosmology, this is simply not enough. We need to do better than that. So the way we take is, well, if we think that this is failing still with the Gaussian streaming model, then the only thing that can go wrong is Gaussian, the Gaussian assumption. Thanks. So we then go about to split the late time distribution of density according to basically the local density of the galaxies, because we know that the late time distribution matter field or traced out by galaxies is highly non-Gaussian. And so the motivation behind it is, well, another thing is that when this field is non-Gaussian, when you compute the two-point correlation function, it's also almost like meaningless, because the two-point correlation function is basically the variance of the field, which is already not complete when the field is non-Gaussian. But then when we split the density in this manner, so illustrated in this 2D or 3D way, it's basically we throw a bunch of top hats filters and a top hat filter of the cosmic web, and then we classify them into low density regions in blue and high density regions in orange or red. And then we cross correlate these bubbles of local underdense regions or with the rest of the galaxy field, or the high density regions with the rest of galaxy fields. So we end up have a spectrum of cross correlation functions. So this is the PDF looks like. Low density, or it's called density split 1, 2, 3, up to high density DS5. So this is the 1D, basically the 1D PDF of the density field traced out by galaxies, smooth at 50 megaparsecs, and it's highly non-Gaussian, obviously. So you can go about to measure this whole spectrum of cross-correlation functions from DS1, which is essentially the void galaxy cross-correlation function, and DS5 essentially is the supercluster cross-correlation function. So in comparison, the two-point correlation function, the conventional statistics people use is here. So you can see the BL feature. You can also see the asymmetry between the void galaxy correlation function with the supercluster galaxy cross-correlation function. And that's an indication that at that scale, the field is not Gaussian. So what's the benefit of doing that? So we can look at the distribution function of the velocity. For this void, around the void regions, you can see there's a Gaussian fit through this histogram measure from simulation. You can see the fit is exceedingly well. And then you can march on to look for gradually increasing densities up to high density regions, superclusters. Still, the Gaussian fit is a good description for the PDF of the velocity. In comparison, if you look at the pairwise velocity distribution as typically needed for modeling two-point correlation function, and then the Gaussian fit is no longer a good description. So this is part of the reason why the model is not doing so well for the two-point correlation function. So now we can provide these ingredients to the Gaussian streaming model and make a prediction for the two-point correlation function, the density split galaxy cross-correlation functions. So you can see there's a whole spectrum of cross-correlation functions shown here in 2D. And actually, there are two layers of contours, one solid, one dashed. One is direct measurement from simulation, another one is the model prediction. You can barely see any discrepancy between simulation and the model prediction, and that's indicating the success of the model prediction. And as again put it for comparison here, in our two-point correlation function, there's some noticeable deviation there. Just a bit more quantitative, if we look at the monopole, quadrupole, hexadecapole for the void galaxy cross-correlation function versus the two-point correlation function, then you can see, let's focus on the fractional error of the model prediction versus the error that is corresponding to a few gigaparsec cubes volume. You see that for the void galaxy cross-correlation function case, the deviation is relatively mild. There's some glitches around 10, 20 megaparsecs at the smoothing scale. But you can see the catastrophic deviation for two-point correlation function just around this region. So with all this in mind, we can then, I think we were confident enough that with its model performance, with the simple trick of splitting density, does perform better. It's more accurate than just taking the two-point correlation function and with the Gaussian streaming model. So we can then perform MCMC fitting with covariance matrix constructed from many realization of simulations, and comparing again the two-point correlation function versus the combination of the void Gaussian cross correlation function and the supercluster Gaussian cross correlation function. The combination of the two will, we find it's sufficient already, and but ideally you want to combine all of them. So you can see the blue contours typically or like outperform are smaller than the contour of the green contour, which is the two-point correlation function. In some cases, they are smaller by extremely large amount. So at this stage, I think we can say that. Oh, by the way, this is we have exact same minimal scale cutoff scale, which is 15 megaparsecs. So for fair comparison. So that comes to the end. I hope I've conveyed to you clearly that redshift space distortion is a way to measure the growth of structure from the cosmic web. And because the non-linearity, non-Gaussian nature of the cosmic web, then we have this splitting density approach that allow us to have the performance of the model being more accurate and therefore pull up more cosmical information from the modeling. Thank you.
2001 paper of you showed the 2001 Redshift Distortion Nature paper by Peacock, and that was based on the 2DF. But I would have assumed that you have a lot more data in STS, and I didn't see anything that was recognizably more detailed or had more information than that particular plot. Am I wrong about that, or did you show an updated version of that?
I didn't show the 2D version, but there's multiple papers using Sloan data to look at the 2D correlation function. And here I just simply show the reduced version, which is the monopole and the quadrupole. So that contains most of the information. But
the reason I was asking for another plot so I could just visually compare the precision that presumably has gotten better.
Yeah, the measurement certainly is there. That's my main point. Hopefully get it clear that typically at this regime we stop here. Look, the data points just stop here, but we're not lack of data. The data will continue down to sub-megaparsec level. It's just we don't have a good enough model. I mean, I'm saying it's maybe slightly provocative following the spirit from yesterday, but I believe this is the consensus, or this is the stage we are living in.
So I have a short question. So you talk about measuring the growth rate in these various density determined slices. Now, if you are in underdense regions, the growth rate is actually slowing down. So aren't you measuring different growth rates and not the global growth rate?
That's a very good point. There is indeed the nonlinear growth rate or the variation of the growth rate depends on the cosmic web structure. And if you look at the framework, the modeling framework here, the Gaussian streaming model, it's ignorant about whether the growth rate is linear or not. But basically, I think there's two approaches here to try to extract the linear growth rate parameter. One can acknowledge, like we do, that voice grows probably slower and supercluster grow faster. Therefore, you end up having a scale-dependent or environmental dependent growth rate. And by modeling the whole spectrum of different pace of growth rate, you can also learn about basically all the same information that you can learn. On the other approach, you use a framework like this to model out the nonlinear growth rate using the same scale, the same information, but then in the end, what you learn back is the pure linear part. It's kind of close to reconstruction. You try to get rid of by forward modeling the nonlinear aspect, and therefore you still learn back the linear part.
Okay.
Yeah.
Thank you very much.